Hi everybody, Peter Rosenthal here. Hope all is well. Hope you had a great weekend and hopefully did a bit of practice of Comm 225. So what we're going to do is, in lieu of a lecture, this week I've put together this little video to go through a problem, question 544 from the text and also on Moodle. And what I'd like you to do is actually look at the problem on Moodle. Since there's more questions, it's a bit more detailed. So let's just start as a reminder. It's Peter Rosenthal here. Here's a picture of me. That's a picture of me on a bike trip in Vermont. And there you see a picture of an old-fashioned library. But just wanted to remember it's Peter Rosenthal, Comm 225, John Molson School of Business. And what we're going to do is we're going to review a problem together. So we're talking here about problem 544. So first of all, just a little review. Recall that last class we talked about 3 different waiting line models. The first one is what I like to call the IGA model, which is a single server, single phase, but it's a little bit more, I guess, easier to remember as a kind of single, as an IGA model. So here you see, here's the IGA right there, and you see that clients can kind of pick any server they want, and there's several independent lines, and they can walk to any server they want. So that's your IGA kind of model, single server, single phase. Then we've got the so-called automatic car wash model right here. There's your automatic car wash model. And again, it's kind of similar to the IGA model, but in this case, we have a constant service time. So why is that? Because it's like a robot. So every single car gets washed at the exact same time. It's a constant service time. And that's the case for the automatic car wash kind of model. And then you've got the bank model. So here's a picture. This is actually, it's an airport. It's a picture from an airport. And the bank model is that you have one really long line, and here you can see the line kind of snakes up and down, and there could be several servers, for example, bank tellers, or it could be people at the airport, ticket agents that are checking you in or whatever it is. So that's the bank model, multi-servers, and we'll talk a bit about that for this problem. And also, here's the formula. So just to recap, these are the same formulas we talked about in class. Remember, there's some formulas here that are applicable to all the models. We've got the basic single server, the IGA model. Here is the automatic car wash model. And here is the multiple server model, which is, of course, like your bank model. All right, so far so good. And here is, remember, when we have a multi-channel model, so just very quickly, we have this table, and we can find out values for P0. If we know what lambda is, over here, if we know what lambda is, if we know what S is, which is the number of servers, we know what mu is, we could then calculate the value for P0 where we plug in the number of servers right here. So just a bit of recap. Let's talk about the problem. So again, take a look at Moodle, and you're going to see the problem on Moodle's got a bit more detail than the problem in the text. So let's look together at the problem. And first of all, there's 3 main parts. So the problem is as follows. Let's just read it together. Here we go. Agents at the security gates at the Hertzfield Regional Airport, I can actually draw on that. Hertzfield Country Regional Airport are able to check passengers and process them through the security gate at the rate of 52 per hour, Poisson distributed. Passengers arrive at the gates throughout the day at the rate of 45 passengers per hour. 45 passengers per hour, and that is the kind of arrival rates. And if you remember in class, we talked about, is this arrival rate, which is lambda, should be in customers per hour, which does seem to be the case. So it says 45 customers per hour. So that looks like a pretty good lambda, and it says the check passengers, the service time over here is 52 per hour. So I think our mu and our lambdas are all good. And it says Poisson distributed. So we know that it is just like the IGA model. And the questions are right here. Determine the following performance measures: average utilization at the gates, average number of passengers waiting in the system, average time passenger spends in the system, probabilities, no customers, 3, 5, and so on, and probability that the arrival has to wait for service. So most of these we've already covered in class, but we'll go through it just as a review. This is kind of the plug and chug kind of part of the question. By the way, the most important part of this question is part C, So please stand by for part C, which is indeed the most important part. Okay, so the first thing, before we go there, part B. Part B, the question is, same idea, we'll look at it quickly here. So part B was the passenger traffic arriving at the airport security gate varies significantly during the day. Flight takeoffs tend to cluster, making passenger traffic very heavy at specific times, while other times there is little or no passenger traffic. At the times leading to the flight takeoff, passengers arrive at the rate of 125 per hour. The airport authority is considering the option of increasing the number of security gates to 4 in order to accommodate this increased level of passenger traffic. Design a waiting line system that can accommodate this increased level. Compare the following performance measures of the new system with the current one. So same idea, similar calculations, but now what they're talking about is kind of a system where you have this, right? And you've got your servers, you've got your servers, you've got your servers, you've got your servers. Here we go. They're talking about 4. Why? Because they're saying that at certain times they arrive much faster at 125 customers per hour. So we're going to look at this case as well. And then C, which is the most interesting one, it's very different than the other kind of problems. Let's take a look. It says that the manager has decided to see the financial implications, here we go, of increasing the number of security gate on the performance of the system. If the cost of hiring an additional security gate agent is $15 per hour, and the cost of keeping a passenger in the waiting line is 50 cents, half a dollar per minute, determine the optimal number of agents they should use, show the calculation. So if you think about this, we'll do this problem together. If you think about this, this is a question where if you have one server, there's a cost associated with that, but the line is slow. 2 servers, higher cost, but the line goes faster. 3 servers, yet faster, but the cost goes up. So the question is, if there's a cost for waiting and there's a cost for service, what is the optimal number of servers that you should have in order to minimize your costs? You want to minimize costs. So we'll do this one together. Very interesting question. Okay, so first of all, let's go back to part A. Let's just review that. So question 1 here. So this is your standard single channel. It's your standard IJ kind of model. We have our lambda here, we have our mu here, and we've got a whole bunch of questions. So let's do that. So the first question was, here's our diagram. Here's our diagram right here, standard diagram. We have mu, we have lambda. It's an IGA model. We want to determine performance measures. Let's do that. The first one was the average utilization of the gate. The average utilization of the gate. So remember we talked about this briefly in class, that utilization is rho. This is the symbol for rho right here. Rho is also known as the probability the server is busy. The probability the server is busy right here, which remember, it's actually the opposite of probability of nobody in the system, P0. Hence, the opposite is probability the server is busy. So very simple, it's just lambda over mu right here, 45 over 52, and we get 0.865 is the answer. Second question, average number of passengers waiting in the system. So number of passengers is L, and the system is LS, and the book calls it L, we call it LS, but it's the same thing. Here's the formula. Formula is given, we plug in the numbers, and we get 6.43 passengers. So far so good. Then we've got next question. I'll just clean that up. There we go. Next question is average time the customer spends in the system. So time is W. System is WS, or just plain W. We have a formula, we plug it in, 8.58 minutes. Very good. So this is kind of a review similar to what we did last class. We know the model, we know the formula, we have lambda, we have mu, and we can plug it in. Next question was, what's the probability of no passengers in the system? This is the opposite of rho. We have the formula for this too, which is right there. 1 minus lambda over mu, which the book also calls I, and I presume that's for idle, probability that the system is idle. And that's simply 1 minus rho. There's our answer, 0.135. I'll clean that up. Next question, what's the probability of 3 customers in the system? So remember last class we did an example of at most 2 customers in the system and so on. This question was the probability of exactly 3 customers in the system, exactly 3. So it's simply just P3. We don't have to do P0 plus P1 plus P2 plus P3. This is the probability of 3 customers. We're going to assume that. So P3, we have a formula for that right there. Plug it in. We get our answer. Very good. So that's P3. P5, so the next question, probability of 5 customers in the system, same thing, it's P5. So we have the formula, we plug it in, nothing more unusual than that. And then the next question was, what's the probability, I'll just clean that up, probability that an arrival has to wait. So this is the exact same thing as the probability that the server is busy. It's just rho, the exact same thing. So this is just another way of saying of rho. So probability an arrival has to wait is the same thing of saying that the probability the server is busy. It's rho, the exact same calculation we did back at the first part of the question. Okay, so far so good. So that's part A. Let's look at part B together now. So part B, so same idea. It talks about here, passenger traffic arriving at the airport security gate varies significantly during the day. Flight takeoffs tend to cluster, making passenger traffic very heavy. The airport authority is considering giving the option of increasing the number of gates to 4. Increasing the number of gates to 4 in order to accommodate this increased level of passenger traffic. Design, just clean that. Design a waiting line system that can accommodate this increased level of passenger traffic. Compare the following performance measures to this new system with the current one. New system with the current one. So here's kind of the same questions, but now we kind of have a multi-channel bank kind of model. And we have a little sketch over here. So now our system looks like this, where we have the 4 servers here. And we've got the arrivals coming in here at the same kind of rates. And we assume that the servers all work at the same 52 passengers per hour. And here, just to clarify that here it's a busy time, so lambda is new. Lambda is 125 passengers per hour. So this is known as the bank model, multi-server. And now we can start doing our calculations. So if we take a look, the first question was average utilization of the gates, same idea. It's rho, and in this case, because it's a multi-channel, again, we have the formula, it's given. Rho is lambda over S mu, which is really the same formula as before. It's just that in the other problem, S was 1. So in this case, there's 4 channels. We have lambda, we have mu. Get the calculation, and it's 0.6. So very straightforward. Next question is expected number of passengers waiting in the system. So number is L, system is LS, and therefore we have the formula for that right here. And here we need P0. And how do we get the P0? We use the table. And I think I've got a table here. There it is. Here it is. So I'll back up. So we need P0. So we use the table where S equals 4 and lambda over S mu equals 0.6. So P0 is 0.0831. Let's see if we can find that. So S is 4 and 0.6. So here's your 0.6. Here's your 0.6 right there. There's your 0.6, and here's your 2, 3, 4. I think I'm right. 4 channels. Whoop. There's our 0.6. I'll just move that into the place. Exactly. 0.0831. Very good. And I'll just put that to select, and I will undo that. I will clean this. That's okay. And we'll go back. And there's our 0.0831 right there. Right over here. So we're okay. So we have P0, 0.0831 from the table. And we've got all our data over here, which is the lambdas and the mu's. And we've got over here, there's 4 channels. We can calculate and we get number of people in the system is 2.84 passengers. So kind of a plug and chug once we get to P0. There's our table again. Next question was expected time a passenger spends in the system. So that's, of course, WS, and its LS over lambda, which we calculate to be 1.36 minutes, kind of a plug and chug. Probability of no passengers in the system is just the P0 that we calculated before from part 2, so nothing new there. Next question was probability of 3 customers in the system, probability of 3 customers in the system. Here, N is 3 because there's 3 customers in the system. S is 4 because it's 4 channels. And if you look at the formulas, you'll see the formula for that it's given is that. Plug and chug, and you get your P3. So I recommend certainly that you take a look at the formula. You may want to try this yourself without looking at the video or the solution, and make sure that you understand where the numbers come from. But it's literally, once you get the right formula, you know your lambda, you have your mu, you have your P0, you have everything, you plug it in and you can get the right answer. Similarly, this question was 5, exact same idea. The formula is a little bit different because, and I think what I'll do is I'm going to just point to the formula sheet very quickly. I'm going to just zoom right back here. Okay, we're going to go really fast to the formula sheet because I want to show it to you. There it is. So here's our multi-server, and look at this. See this formula? So depending on whether N is bigger than S right here, which was the case for 3, because N is 3, and S being number of channels is 4. And in this case, N was 5, probability of 5, given 4 channels. So the formula is a bit different depending on whether your N is bigger than S or N is less than S. So hopefully that's clear. It's just double check the formula and I'll just go back. I'll just go back to where we were. Okay, I think we're doing okay. So far so good. There it is. 3, 5. Perfect. Okay, so we, again, plug and chug. Once you get the right formula, you're kind of good to go. Then, probability in arrival has to wait for service is the same as the probability server is busy, which is 0.6. And then, here's a note. With multi-channel, the average time a customer spends in the system is much less, 1.36 minutes versus 8.58. So the question was, you want to comment on the difference between the single channel and the multi-channel. And of course, the multi-channel performs much, much better where customers spends much less time waiting or in the system. And also, if you look at this, just compare the numbers, the probability of the server being busy is much less, 60% versus 86%. So in the first case, there's a kind of a high probability your server is busy versus in the 4-channel case, it's a much less probability. So I hope that's clear. And of course, if you have any questions, don't hesitate, let me know. So the next question, which is the most interesting that hopefully you can spend a bit of time on if you're watching this video. The next question is, let's review that together. So the manager has decided to see the financial implications of increasing the number of security gates on the performance of the system. So it's kind of a little bit like in the last question, they chose randomly 4 agents. But is 4 the right number? What if they chose 3? What if they chose 6? Is 4 the right amount? So in order to come up to that answer, we need to know some cost information. So we know that the cost of hiring an additional security agent is $15 per hour. So for every security agent, assume it's $15 per hour. That's what we're going to do for this problem. Every security agent is $15 per hour. So 2 agents is $30 per hour, 3 agents is $45, and so on. And the cost of keeping a passenger waiting in line is $0.5 per minute. Now, I don't know why they give the information in dollars per minute, but what we're going to do is we'll convert it to dollars per hour, and it's equal to $30 per hour, right? So $0.5 per minute is equal to $30 per hour. So now we have hours and hours. And if you think about it, if we can calculate how long customers wait, what they say is the cost of keeping a passenger waiting is $30 per hour. So if we can calculate that time in line, or how many people are in line, then we can calculate that. So the cost of keeping a passenger in the waiting line is 50 cents a minute times the number of people in line, we get a cost. We can compare that to number of servers, 2, 3, 4, 5, and then we can kind of find the optimal situation. So we'll do that together. And I wanted to also mention to you, just go to the next page, we'll take a look at that. How do we do this? So how do we go about this problem? So what we're going to do is we want to find out optimal number of agents to minimize the cost. We are going to balance the agent cost, so again, $15 for one, $30 for two, and so on, versus the wait cost. We know the agent cost is $15 per hour, and we know the passenger wait time is $30 per hour. That's all given. So we're going to do a little analysis. If we have 3 agents, 4 agents, 5 agents, 6 agents, 7 agents, and so on, what's the right number of agents to come up with the lowest total cost? So as we said, 3 agents is 45, 4 agents is 60, 5 is 75, and so on. We're going to calculate the LQ, given whether we have 3, 4, 5, or more agents. We know that LQ is the number of people in line times 30. And then we're going to calculate the total cost of the LQ and the agent cost. And the one that gives us the minimum is the answer. So that's the strategy. It's a little bit different than what we did in class. But if you think about it, it's kind of logical and it uses all of the tools that we learned in the previous kind of problems. Okay, so how do we go about that? So the first thing I wanted to mention is that, I'll just clean this up. Why don't we start at 2 agents, for example? Why don't we start at 2 agents? Well, the reason why we don't start at 2 agents, we start at 3 agents, is because we know that we have a mu and we have a lambda. And we know that our lambda is 125 and we know that our mu is 52. It's given. So we need to have lambda. We need to make sure that our lambda is going to be less than, we have to make sure our lambda over here, see this? We have to make sure that our lambda is less than number of channels times mu. Why is that? Because if it wasn't the case, then we would have an infinite line. If you think about it, lambda, which is the arrival rate, is 125. So let's clear this up. Let's look at it another way, just to clarify that. So lambda, arrival rate is 125 passengers per hour. And mu is our service rate at 52. So our lambda is going to overwhelm the servers at 52 if there's only one server. If there was 2 servers, let's say if it was 2 times 52, it would still overwhelm because 125 is greater than 52 times 2, which is 104. So still not good with only 2 mu's. Let me undo that. Just clear that. If you have 3 mu's, which is 3 servers, if you have 3 servers, so it's 3 times 52 is 156. So 3 times 52 equals 156 versus lambda, which is, lambda is of course 125. So this is okay. So that's why we start at 3. There's no point in starting below 3 because you need to have at least 3 to accommodate the 125. 3 times 52 is 156. You can't have a situation where your lambda is greater than your mu, because otherwise you would have an infinite line. So that's the reason why. So hopefully that's clear. If it's not clear, let me know and I will clarify that for you. So that's why we start at 3, because you need to have basically, I'm going to write this down. You need 3 times 52, which equals 156, greater than 125. And this is your lambda here, and this is your mu, and this is your number of servers here. Number of servers. servers. So our analysis is going to be 3 servers, 4 servers, 5 servers, 6 servers, and so on. There's no point in doing 2 servers because that won't work. It's going to have an infinite line. We're going to start at 3 because that's where we exceed the lambda. And the question is, where do we stop? We do 3, 4, 5, 6, 7. Where do we stop? Well, it's a very good question. And I will show you as we do this problem where we stop. So we'll just clean that up. And we are going to start the problem. So what we want to do next is, let's calculate some LQs. So the first thing is, for 3 agents, we can get P0. We've done it before. We use the table. We have lambda. We have mu. We can calculate our P0, and therefore we can calculate our LQ for 3 agents. So there's our LQ for 3 agents. For 4 agents, exact same process. We find a P0 for 4 agents. We calculate our LQ, which is right here, for 4 agents. If we have 5 agents, and when we say 5 agents, we mean, of course, 5 servers. Same idea, we calculate our P0. We calculate our LQ once we have our P0 over here. And then we can finish our table. So look at this. Here's the number of servers or agents, which is 3, 4, 5, or 6, and so on. Okay. Here's our agent cost right here. So agent cost is nothing more than 3 agents times $15 an hour, 4 agents times $15 an hour, 5 times, and so on. So here's our agent cost. Clear that. Here is our LQ. Here's our LQ, which we calculated just before using the P0 and using the formula for LQ for a multi-server, which is either 3, 4, 5, or so on. Okay. Then, once we have our LQ, we can calculate our waiting cost because we're given $30 per hour. $30 per hour is given. We multiply that by the LQ, which is the number of people in line. $30 an hour is an assumed amount when you're waiting in line, sort of the effective cost of waiting in line. Could be sort of like a passenger dissatisfaction or something like that. So people can sort of do surveys to find out that number. We do the math. So this is nothing more than LQ times 30 in each case. And then what we do is we add up over here the LQ. So for example, this is equal to our cost, so it is to LQ, associated to LQ, plus the cost of the agents right there. So the 45 plus the 79.20. To clean that up. Same thing for each of the different number of servers. And if you notice, look at this. Look at this. So our cost here with 3 agents is 124. Remember, there's no point to doing 2 agents because we have an infinite line building. We have to make sure that that does not happen, and we want to, and therefore we will not calculate that. And then what we have is the cost goes to 73, so it drops when we have 4 servers. Then when we have 5, look at this, it starts to go up again. 78. At 6, it starts to go up again. And if you were to do the math, which you don't have to, at 7, 8, 9, and so on, this would keep going up in cost. So therefore, the process is you do 2 or 3 calculations, and the answer lies just before the cost starts to go up. So it's right over here. So look at this. So with 3 servers, 124. At 4 servers, 73. At 5 servers, 78. Cost starts to go up. So therefore the answer is 4 servers. That's where the cost is minimum. And that is the answer right here. That's the answer right here. So I hope that was kind of helpful. I hope that was clear. This question was really good. Super good question. It's sometimes will show up on exam. I have seen it before. But if you kind of know the process now where you're sort of looking at the cost of adding agents or adding servers versus the cost of waiting in line, you do this kind of little table and you're going to see your minimum cost over here. And that's basically how it's done. That's the logic. So I hope that helps. Thanks a lot. If you have any questions, of course, send me an email. And remember to come and see me during the office hours or come and see me after class. I'd be more than happy to help you with that. And just as a reminder, just a second, hold on. As a reminder, yep, it's Peter Rosenthal. Here's another picture of me. Look at this. See, there's snow already. So this was from last year, if I remember well, going for a run on the mountain. Snow is coming, so stay warm. And again, I hope you found this helpful. Let me know what your thoughts are. Was this video good? Was it kind of complicated, or was it helpful? Let me know. I'd like to know. Otherwise, we'll see you next class. Take care, and bye for now.